Today we are going to see about universal verification methodology. It's nothing but UVM. So system Verla. So here also we are going to use the same system Verla, but here we are going to follow some methodology. Okay, some set of standard things we are going to use, and we have many packages, many base libraries is available in UVM, which make easy to do the verification process. So we will see one by one. So these are the verification challenges we are facing. So finding bugs early and fast in design lifecycle. That means so design and verification start at the same time. We are not waiting for design to complete and then we are not going to start the verification. So if we do like that, it will take more time to bring the IC into the market. Okay. So what we are doing is, while the design starts, at the same time they will give the spec to the designer and also the verification engineer. So based on the spec, we have to develop our verification components. Okay. So once the design is ready, we have to write the test cases and we have to verify each and every scenario or specification which is given. So this is one schedule we have. Then it increases the complexity in design. So when the complexity of design increases, the verification process also increases. We have to check more combination of inputs and we have to check the error scenarios also. So that is challenge we are facing. That is next point is limited time. That means the design cycle completes at the same time we have to complete our verification process. So the limited time is given and limited resources available. That means here we can't reuse on in a system developed test bench if we are not able to take that and we are not able to reuse in efficient way. And also we have to write our own methods for implementing some functions, everything. If you want to do comparison, we have to write our compare function. But in UVM, we have all the methods inbuilt. So in system development, we are facing another challenge. Verification is the available resources limited. Then next point is always more possible test scenario to test than available time than resource. Same thing. So in the given time period with the available resource, you have to check the more scenario of the design. So these are the challenges we are facing in the verification. So what is the need for standard methodology? So traditional method does not scale up or enable views across verification for complex design. So we can't take normal example system will not test bench. So each one of you will design in your perspective. Okay. So if I take any one of your code, if it is simple code, I can able to understand and I know where to modify for my RTL verification. It's a complex one. It will take more time to understand your perspective, how you will design that thing. So for example, if we take we can pass the interface handle in system verilog through the function loop. That is one way. Another way we can uh, set in a config DB and we can get from config DB. So based on your idea or logic, you can design in your way. So there is no standard method. I can't able to use your score effectively for my design. So there we are lagging. Okay. Then next point, verification is increasingly become critical and complex. So when the design is, become complex, the verification process also uh, complex for identifying the bugs for a critical design. So there is a need to speed up overall process and increase the efficiency of project to project. So for that we need this standard methodology. If we have a standard methodology, we can what we done for a one project, we can able to use for next project. Same thing we can use. So it will be efficient when you use with a standard methodology. So what is a verification methodology? So it is nothing but it defines a set of standard or process that enable efficient verification. So that means it is we have some standards. For example, here in UVM, we have phase concept, phases. So here, for example, the component everything will be created in the build phase. There is a phase build. Okay. So in that we will create each component. Then there is a phase connect phase. So in that we will make connection between the components or TLM ports, those things. Okay. So the same way, run phase is there. So in run phase, the actual process will be happening. So here we are following some standards. So if I want to modify anything during the runtime, so I will go to the run phase and I can able to modify that. If I want to create anything, any component newly means, I know it is we will create in the build phase. So I can go to the build phase and I will put my create method over there. So the next point is it address automation, abstraction, and reuse. So here in UVM we have automation. That means we have lot of predefined methods. Okay. So for example, we have a compare, load, copy. Okay. Those methods are available in by default. Okay. So when you call that, automatically that process will be happening. So here it is one advantage. Then abstraction, in the sense it is if we program in a high level of abstraction, the low instructions or process will be automatically happen. One example is UVM do is there. Okay. So UVM do is one macro is available. Okay. When you call that, automatically it will create a transaction and it will randomize and it will send the transaction. Okay. The three process will be automatically done when you call UVM. So like it gives the highest level of abstraction. Okay. So when you do the command, automatically lowest level will be taken by the tool. Then reuse. So if you follow a standard methodology, standard basis, so we can able to reuse this testbench architecture for the further verification process. Then this is the history of verification methodology. So here Vera is the used by synapses. Okay. So for verification. Then V is a verification language used by the Cadence. Okay, in early days. They follow synapses. They follow RVM, reference verification methodology. Okay, they follow this methodology. Then Cadence they followed ERM, reuse methodology. Okay. So when system Verilog introduced, so early we use different languages, one for verification and for design. We use Verilog for design, and for verification they synapses they used this Vera language. Then Cadence they use C language. Then it is quite complex to use two different languages. One is for design and another is for verification. They introduce system Verilog. In system Verilog we can also do the design. Also we can use this for verification. When system Verilog introduced, they the help of system Verilog and the methodology which they follow RVM, they derived this VM, verification methodology manual. VM is verification methodology manual. So this AVM is used by the mentor. Okay. So mentor they derived AVM methodology and they follow AVM, and also URM. That is a universal reuse methodology. Okay. So it is taken from system Verilog and also ERM. So they introduced URM, and they some of the times they follow this one. Okay. Then after few years, they derived OVM. Okay, OVM is Open Verification Methodology. So few concepts from AVM and URM, they created this OVM and they follow this OVM methodology. So then later VMM. So VMM we have a RAL concept. Okay. So few concepts from VMM and few concepts from VMM, they derived VMM 1.2 version. Then finally, now everybody uses UVM, Universal Verification Methodology. So now every company, that is Synapses, Cadence, Mentor, everywhere, a common methodology if you follow, it will be easy to reuse. Okay. So UVM, that stands for Universal Verification Methodology. So UVM is based on the previous methodology, OVM 2.1, this version, okay. 2.1.1. So it is hybrid technology that originates in Mentor's AVM, Mentor's Cadence OVM, then Versity's ERM, and Synapses VMM wrapped. From everything, from those things, finally we derive UVM, and it is adopted as IEEE standard 1800.2 in November 2017. So these are few highlights of UVM. So here we have a constraint random and coverage driven verification. So constraint random, you know, right? So in system builder also we are using constraint random and coverage driven verification. Same thing we have in UVM. Then configurable and flexible test benches. So configurable and flexible test bench means we can able to design number of slaves and number of masters, and we can decide whether the agent is active agent or a passive agent. That means an agent consists of driver, sequencer, and monitor. Okay. So when we want to access as the active agent, these three will be enabled: driver, sequencer, and monitor. When I want to use as a passive agent, only monitor will be available. So that configurable facility we have in this test bench. So the transaction level communication. So to transfer the transaction from one component to another component, we have TLM ports here. So in system log we used mailbox, right? So in the same way, here we have TLM ports for transferring the transaction from one component to another. Then here we have a standardized messaging. So messaging just to display. Okay. Here we can able to display from which file I am displaying this, which line I am displaying this, and we have a verbosity level. Okay, whether I want to display the statements during the runtime or not, that we can decide. Okay, by giving the command, inline command. So that we will discuss in detail while seeing messaging. Then libraries which contains of predefined classes. So in UVM we have a package. Inside that we have a lot of libraries or methods available. Okay. So by extending that only we are going to implement our test bench. Then predefined macros. So for display info macro is there. Okay. So there are a lot of macros. I told, right? UVM do is a macro. So lot of macros are there. You can directly use those macros in the design. Then register layer. So this register layer is used for verifying the registers and memories which is available in the design. Okay, that's a separate concept that we will see at the last. So it's a concept used for, especially used for verifying the registers and memory. Then here in UVM, separation of sequence from the test bench. So here test bench architecture will be a standardized one. Okay. So sequence is separate one. So we can write the sequence for the for our own design. Okay. So we can use that sequence for the some other test bench also. Okay. So this is one advantage we have. So UVM class library. So I told, right, library which consists of predefined classes. So in UVM class library, it provides all the building blocks that are required to build modular, scalable, reusable verification environment. So this library consists of all base classes, okay, then utilities and macros to support the entire verification process. So all base classes in the sense for our test bench architecture components like UVM driver, so that is available by default in the package. Okay, so you have to just extend that, and you have to use the driver. Okay, and you see console is available. So in the same way, everything is available by default. What we have to do, we have to extend that, and we have to implement our concept. So, so in order to use UVM library, user need to do these steps. Okay. So first thing is you have to compile UVM package that SV file. Okay. Before doing the simulation, you have to compile the code, right? So during that, you have to compile the UVM package, so that we can able, if we use this package inside the code, we can recognize that it is available in the package. Then import UVM package into desired scope. So you have to import the package. Then only you can able to utilize those macros or that components, everything. We include file that contain UVM macro. So UVM macro is separately it is available. So if you want to use the macros, you have to include the UVM macro also. So next slide, I will see one small example. Okay, simple hello world program using UVM. This you can note it down and you can try it in EDA playground. Okay. So this is this is tick include UVM package.sv. Okay, here we are just including the UVM packages inside the code. Okay, so that the compiler will start from the top and it will do the compilation. So we are including the packages. So compiler will check all the packages available in the UVM. Then here is the actual code module, hello world, main module. Okay, inside that we are importing UVM package. Okay, import is a keyword. Import UVM package scope resolution star. Okay. That means, so whatever available in UVM package, that star means everything. Okay, we are importing here, so that we can able to effectively we can able to uh, utilize the libraries or macros which is available inside the package. Then you have to include macro, UVM macro is available, okay, in the library. So that also we are including. Tick include UVM macro.svh. Okay. So example, here within this initial, okay, here I am using tick UVM info. Tick UVM info is nothing but a macro. So when I include this macro, then only I can able to use this macro. So that I am including this macro step. So tick UVM within the bracket. So here from which stroke I am printing. So that you have mentioned here. If I want, I am displaying from driver means I can give a driver here. Okay. I am displaying from top means you can give top here. Okay. So actual message what I have to print, that is mentioned in this double quote. And this third one is, this is the verbosity element. UVM low is given here. So that we will discuss in detail the forthcoming slides. Okay. So based on the verbosity, we can, it gives the control whether I have to display this or not. Okay. That is called verbosity here. So UVM test bench basics. So the test bench is generally divided into static and dynamic components. So here static and dynamic in the sense, I don't think that So based on the memory. Okay, it is generally we are divided into static and dynamic. Static means it will constant throughout the simulation. That's why it is called static. Dynamic means during the simulation, it will change. Okay, the nature of sequences that will change. That's why it is mentioned as dynamic. Okay. So static components forms the test bench hierarchy. Then remains throughout the simulation. For example, driver, checker, monitor, scoreboard. These are all the static components. Throughout the simulation, it will be constant or static. Okay. It won't change. The dynamic components forms the stimulus. Okay. So static components are these components. It is used to form the test bench hierarchy. Okay. The dynamic component it forms the stimulus. Stimulus in sense you know right input values okay, are generated dynamically. For example, transactions and sequences. So this will be the components. It will be constant for the simulation. But if we run the test register write read, so register write sequence will pass, and then read sequence you are passing. Okay. So sequences are varying or changing dynamically during the simulation, but these are all constant throughout the simulation. Based on that, we are classifying this as static. These are dynamic. So this is the simple UVM hierarchy diagram. Okay. So on top of UVM object, we have UVM root and UVM null. Okay. So these are the classes which is available defaultly inside the library. Okay. So here UVM object is available by default. Okay. This UVM object that contains print method, okay, compare method, clone method, record method. Okay, everything methods are available in the UVM object. Okay. So when you inherit this one, automatically whatever present inside the UVM object that will available in the UVM transaction. Okay. So this UVM transaction also available inside the library. So UVM object they are keeping as a base class. Okay. From that they derive UVM transaction. So from UVM transaction they derive UVM sequence item. Okay. So here some additional concepts they introduced. They add sequencer groups. Okay. So that means in sequence item they are adding some inbuilt methods that is able to communicate between sequence and sequencer. Actually, ID will be created for each sequence. Okay. So it will internally this transaction or this set of values is have particular ID. It will transfer to the sequencer. Okay. That way, internal for some hooks will be added in the sequence item that will not available in the UVM transaction. Okay. So when you want to create a sequence item, okay, in system Verilog, if you it's nothing but a sequence item you created, right? Or package, you want to create packet, not a package, packet. Okay. So class packet, we will define some set of properties and methods, right? So here you have to use this UVM sequence. So UVM my sequence item is extends from UVM sequence item. Okay. So the input method will be available in my sequence item. Okay. So in my sequence item, I can define my inputs and what are the control bits I have. I will declare those things, and if I want to some methods, I can write that methods. Okay, input and methods we will write in a class, right? So that should be extended from this UVM sequence item. Then from UVM sequence item, we are creating this UVM sequence. Okay, this UVM sequence is available by default in the library. So when you write the sequence, you have to extend from this UVM sequence. Okay, so if I want to write the write sequence, okay, so class write sequence extends UVM sequence. Okay, so I want to create a sequence item in my test bench. I have to extend my sequence item from UVM sequence item. That means class my sequence item extends UVM sequence item. Then I can write my properties and methods. I want to write my sequence in my test bench. Class my sequence extends UVM sequence. Okay, in that I have to write my actual sequence. Inside that I have to write. Okay. So here it is I told right. This my UVM sequence is extend from UVM sequence item. Okay. So whatever we have inside the UVM sequence item, that will be available in UVM sequence. Additionally, here they are added body method. So body method is a important one. Here actual process we are mentioning inside the body method in this sequence. Okay. So it is additionally added compared to this UVM sequence item. That's why for creating sequence, we are extending our sequence from UVM sequence. Then in the same way, so this is uh, transactions, sequence item, sequence. These are dynamic in nature. Okay. So static components that also derived from UVM object. From UVM object, we are deriving UVM report object. Okay. So UVM report object, whatever you have in UVM object, that methods copy, compare, those methods are defaultly available in UVM report object. Here additionally, they are adding some reporting infrastructure for displaying. Okay, I want to display in uh, hierarchic order. Okay, or in tree order. Those things you can do when you inherit from UVM report object. Okay. So further, from UVM report object, we are extending UVM component. Okay. So this in UVM component, we attach static hierarchy, phase, and configuration support. That means I told right. We are here. We are using phases. So in UVM component class, defaultly it has the build phase, connect phase, run phase, everything. Okay. And also we have some configuration support. We have a set method, set config, get config, okay, get full name. Those methods are defaultly available in UVM component. Okay. So what we have to do, I told right some static components like driver, checker, monitor, scoreboard. Those things we have to extend from this UVM component, and we have to do develop our verification environment. So this is the test bench architecture, simple test bench architecture of UVM. Okay. So test bench is a top code. Okay. So what we have to do here, we have to instantiate our DUT. Okay. Then interface and the test. Run test we have. Okay. Run test. The run test we will mention the which test we have to run. Okay. So run test automatically. So this test, okay, uh, it decide which sequence has to run in which sequencer. Okay, if, for example, in test bench, I am mentioning there is a run test. I am mentioning um, register write read test. Okay, so when I mention register write read test, so inside the test, it will decide there are different sequences available. So there is a write sequence, read sequence, reset sequence, everything will be there. So based on the test, first reset sequence will pass to the sequencer. Okay. So it will through the driver, it will through the interface, it will send to the DUT. Okay. then it will pass the write sequence. So write sequence pass to the sequencer. So from sequencer to driver, it will transfer to the TLM port. In the transaction level only it will communicate. Okay. So it will reach driver. Then in driver, you see the transaction is converted into a interface level, spin level. Through the interface, it will reaches the DUT. Okay. Then read sequence it will send. In test we will map read sequence with this sequencer. So this sequencer send the read transaction. Here it is converted to pin level and it is sent to the DUT. So it is a read, right? So it will send the response. Okay. So that's response will monitor. Monitor will receive in the pin level. Then it will convert into a transaction and it will send to the score code. So the monitor will always monitor whatever the inputs going to the DUT and outputs coming from the DUT. Okay. So whatever you are giving at the right sequence, that also it is monitored by the monitor, and in scoreboard it will store the write value. During the read process it will capture the read value, and here we are comparing and it will show. Okay. So this configuration I told, right, whether we have to create this agent as an active agent or passive agent, so that is defined by this configuration. And also interface we can set in this config DB, and we can able to get here actual interface I will set here. Okay. So driver and monitor need this interface. So from get method I can able to get the interface handle, I can able to send the data. Here I can able to capture the data. So that I will explain in detail when we see this configuration and testbench architecture in detail. Okay. So here the difference is uh, when you compare with this system Verilog test bench. So in system Verilog test bench, what we will do, we have the test bench top will be there. So inside that we will call program. Okay, program block test program block TB you will call. Okay, so when you call this TB, so automatically that TB will enable the environment. Okay, now I am explaining for system Verilog. Okay, system Verilog we have a top module. Inside that we will initiate the program block. So when that program block will enabling the environment. Okay, so in the environment we have generator, then driver. Okay, so in the generator we have to write the different test cases. Okay, so how we can get the test case? By using dollar value dollar plus x in the top, we can get the test case, and then based on the test case the generator will generate the sequence and it will pass to the driver with the help of a mailbox. Then driver will drive these signals. Okay, but here the architecture is different. Okay, here we are not going to use the program block. Okay, because to avoid the race condition we use the program block in system Verilog. But here we are using different phases. Okay, so in build phase all components will be built up, and then connect phase connection happens, and then run phase only actual run process will happen. So here this test is a class. Okay, so here when you call the test, automatically then it will create the environment and it will build the hierarchy. Okay, so this sequence is separate from the TB. So sequence we are writing separately for all possible inputs. Okay, so inside the test we are mentioning which sequence has to go to the sequencer. Okay, so based on that it will drive the value and it will reach the DUT. The process will be happen. So available UVM components all are extended from the base UVM component. So I told, right, this is the hierarchy. We have base classes, UVM object. From UVM object, UVM report object is derived. From the UVM report object, UVM component is derived. From the UVM component, they derive UVM driver, UVM sequencer, UVM agent, everything is derived and it is kept inside the UVM library. Okay, so if you want to create some these components, you just extend from this UVM driver. I want to create this driver. Okay, so what I have to from class my driver extends UVM driver. Okay, I want to create my sequencer, means in the test bench class my sequencer extends UVM sequencer. Okay, the same way these are the static components available by default in the library. So from this we can derive our own test bench components. And the dynamic components, dynamic objects are available UVM class to model sequence and transaction items. So UVM sequence item and UVM transactions are available by default in the library. Okay. So UVM object is the top. From UVM object we are deriving this UVM transaction. This UVM sequence item is derived from UVM transaction and UVM sequence is derived from UVM sequence item. This happen defaultly and it is kept inside the library. So in my test bench, I need this sequence. Okay. So how I can write this sequence? The class my sequence extends UVM sequence. Okay. So I want to create my sequence item. So how I can write class my sequence item extends UVM sequence item. Okay. So in that way, we have to derive our components or object for the test bench. Okay. So here these are all called statics because it won't vary. Once you create it, throughout the simulation it will be constant. But sequence and sequence items will be varying. So based on the test, those things are changing, right? So that's why we are calling this as a dynamic objects. So next is transaction level modeling, TLM course that we will discuss tomorrow.